Good morning, everyone. I'm pleased to present our work towards perception-informed latent HRTF representations. This is a joint work with Andrew, Ruohan, Paul, Zhiyao, and Ishwarya. Okay, first a quick refresher. What is HRTF? HRTF stands for Head-Related Transfer Function. It models the acoustic filtering effects of a listener's head, ears, and torso to enable 3D sound localization. On the right figure, I showed an HRTF magnitude plot along the mid-sagittal plane where the azimuth angle is 0, showing how spectral patterns changes with elevation angles and frequencies. As we are all shaped differently in ear, head, and torso, HRTF is unique to each person. And HRTFs are widely used in virtual spatial audio rendering so that we can place the virtual sound sources in 3D space. It has wide applications in headphones, AR smart glasses, VR headsets, and so on. It's important that these systems should be personalized for your HRTF. Otherwise, the 3D sound experience may not be accurate. Okay, how do we get your HRTFs? The first way is, of course, to measure them. However, this process is complex and requires specialized equipment from anechoic room to head motion control. As you can imagine, the whole process is both time-consuming and resource-intensive. Now, this is where AI comes into play. The goal is to use AI to predict a person's HRTF so that we don't need complex measurement equipment. There are two mainstream models for this. Both models follow an encode-decode process. The latent space is what we denote as Z here. It represents the intermediate complex representation of HRTF. For training and evaluation, most existing models rely on L2 spectral distance, comparing the reconstructed HRTF with the ground truth HRTF based on the spectral reconstruction error. And AI models aim to minimize this spectral reconstruction error, but they may produce HRTF with low spectral error, but this is still not what we need. What we need is perceptually plausible HRTFs to create a natural sound experience. But we still don't understand whether this low reconstruction error give us perceptually plausible HRTFs. And this gap motivates us to go beyond just spectral reconstruction and incorporate perceptual considerations. So our goal is to learn latent representations for HRTF models that more accurately reflect perceptual correlation to enable better HRTF personalization for unseen users. To achieve this, we must first study how well existing latent HRTF representations preserve perceptual relations. And since there's no benchmark for this, we introduce several metrics to evaluate this. And we then propose a method to improve on this benchmark. And then we demonstrate practical use for HRTF personalization. Okay, now let's dive into the first question. How well do existing learned HRTF representations preserve perceptual relations? To investigate this, we need to first understand what are the perceptual aspects we care about for HRTF. So backed up by many perceptual studies, the perceptual benefits of your personal HRTF has been summarized in these three aspects. We have reduced coloration, improved externalization, and enhanced localization. And now we understand the concept. The question becomes, how do we mathematically model this before study if AI capture these concepts? So in this study, we resort to computational auditory models. And specifically, we took the MATLAB toolbox called Auditory Modeling Toolbox, which models the human perception and behavior when humans listen to binaural audios. More specifically, for coloration, we use this predicted binaural coloration. And externalization, we use auditory externalization perception. Localization, we use difference of root mean square error in polar angles. And in short, these are PBC, AEP, and DRMSP. And we call this objective perceptual metrics. Okay, for setting up the experiments, we use the SS2 HRTF database. It contains over 1,000 measurement locations and very high sampling rates, and it in total measures 78 subjects, where we use 65 for training and 13 for testing. And we first train our AI models with spectral reconstruction error for HRTF data to get the latent space. And then we compute the pairwise latent distance across subjects. And we also compute the pairwise perceptual distance across subjects. So this figure shows the alignment between the latent space and perceptual metrics. Here we take PBC as an example. You can see that many points are scattered around, showing the relationship between latent distance and perceptual distance. To quantify the alignment, we calculate the Pearson correlation, which measures how well the latent space corresponds to perceptual differences. A higher positive correlation indicates better alignment with perception, and a perfect correlation would give us a value of 1. However, as shown in this table, the actual results are far from 1, even on the training set, suggesting that there is a significant gap. So this leads us to conclude that minimizing spectral distances, while effective for numerical accuracy, it leads to limited perceptual correlation. Then the question becomes, how do we align latent HRTF representations with perception-informed space? So we built our method on top of the existing models where they use basic spectral distance as the training objective. So if our objective perceptual metric is differentiable, then the question, this problem is easy. We just add a straightforward perceptual loss. So we compute the perceptual metric out of the HRTF and then calculate the perception distance to minimize that. But this only applies to PBC, which we implement that with PyTorch. The difficult part is that if the perceptual metric is not differentiable, then we cannot apply the perceptual loss anymore. In this case, we resort to metric multidimensional scaling. So we propose to use this MMDS method, which is a dimensionality reduction technique that preserves the distances between points in the original space while mapping them to a new optimized space based on these distances. So for example, the distance matrix shown here, it provides the pairwise distance between these 5 dots. And in the new space where we optimize to, this space maintains all the pairwise distances through MMDS algorithm. So the key idea is that the distance matrix provides a map, and the algorithm builds the space based on the map. So for our method, we first compute the pairwise perceptual distance matrix, and then use MMDS to optimize the new space to figure out how different HRTF relate to each other in this space. And we call this space ZMDS. And this space has the same dimension as our original Z space. Then we compute the L2 distance between the ZMDS and the Z. This provides the MMDS supervision, and we call this alignment loss. So please note that this method can also be applied to differentiable metrics. So overall, our pipeline shown as here, where we have 2 losses. First is the perceptual loss, but this only applies to BBC. And we have another alignment loss through MMDS supervision, and this applies to all the metrics we want to use. Okay, let's see some results. So the first results on the objective perceptual correlation evaluation on the PBC metric. As the neural representation model cannot fit perfectly on the training set, so we first compare the correlation learned by all methods versus the baseline method on the training set. So you can see that our method achieves a near perfect correlation on the training set. So this shows that our proposed method achieves better alignment with perception-informed space. Then let's look at the result on the test sets. We still see some improvements, so the perceptual correlation learned in training sets transfer to test subjects. And these are the results for the externalization and localization metrics. We also observed the improvements over these two as well. So yes, our proposed correlation improvement method generalizes to externalization and localization. We have more comprehensive results and ablation studies on the poster and paper. Please check out. Okay, to then demonstrate that our learned representation is practically useful, we use the downstream task of HRTF selection. So for each of the 13 test subjects, we select the nearest HRTFs from the 65 training subjects based on the learned HRTF representations, and we compare our methods versus the baseline method that just used L2 as the training objective. So we can see that based on our selection method, we achieve a better DRMSP metric. So this shows that the HRTF selected by our method yields a lower perceptual distance, but with slightly higher spectral distance. This means that our method selects a HRTF that is more perceptually better. So again, we have more results on the poster that covering other metrics as well. So with these results that our method achieves better perceptual alignments, we still acknowledge some limitations. First, our objective metrics may not reflect listening experience totally. So the future work, of course, we want to have more subjective listening tests. And our methods, we believe it can also be extended to binaural audio synthesis, reproduction, and so on, basically work in the audio domain. So for spatial audio modeling, most of the existing methods are viewing this as an engineering problem. However, we envision that incorporating physics and perception is just as crucial for creating more realistic spatial audio experience. And we believe our work takes a step towards supporting this broad vision by integrating perceptual components into this HRTF representation learning. Okay, that's all for my presentation. Please check out our posters for more comprehensive results and analysis. Thank you, and I'm happy to take any questions.